Good morning, everyone. So today I'll be presenting our work on design and implementation of a verify interpreter for additive manufacturing programs. So let me start by explaining what additive manufacturing is. To do so, I will draw a contrast between conventional manufacturing and additive manufacturing. Conventional manufacturing falls under the category of subtractive manufacturing, where parts of the tools are removed. Some examples of conventional manufacturing are milling, lathe, and drilling. Additive manufacturing, on the other hand, deposits materials layer upon layer in precise geometric patterns to create tangible objects. And since there is addition of material going on instead of removing the parts, it's called additive manufacturing. And there are typically 7 types of additive manufacturing techniques, namely material jetting, wet photopolymerization, binder jetting, material extrusion, directed energy deposition, sheet lamination, and powder bed fusion. In this work, I'll be discussing the material extrusion, wherein material or the filament is extruded from the nozzle and melted to synthesize a 3D-dimensional object. Just like any physical processes, additive manufacturing also has different sources of errors, which are classified into 3 categories. Software error, where errors can arise in the toolpath planning software. Errors can come from the post-processing software as well. Kinematic and geometric error, which includes errors coming from collision between the printer head and the object being printed, and the thermally induced error. Configuration error.
Can I just ask a quick question? I didn't quite catch you mentioned extrusion.
Yeah.
Even if I didn't really quite catch what it was.
Oh, sorry. Yeah. So extrusion is basically the technique wherein filament is it's a finite deposition printing. So a filament is extruded from a nozzle, and then you heat the filament and melt it, and then you deposit it in a pattern which is specified by the CAD model. So yeah, material is extruded, and then you heat it, and then.
So is that related to? I guess this is obviously a lot bigger than 3D printing, but is that 3D printing an example of that one?
Yes, it's a finite deposition.
Right. Okay. Yeah. But it could be other materials.
Exactly.
Right.
Yeah. So 3D printing is just one type of material extrusion.
Right. Okay.
Right. Yeah. Good. Yeah. So the third category of error is the configuration error, where the errors can arise from human errors in specifying coordinate information, or incorrect specification of tool offsets and fixtures, or poor selection of feed rates, spindle speed, or unwise choice of the order of machining. In this talk, we'll be focusing on just the errors arising in the toolpath planning software. So there are 2 common approaches for validation in additive manufacturing. Those are simulation with visualization, and physical examination of the artifact after fabrication using destructive and non-destructive testing techniques. And each of these techniques have their own set of limitations. For example, the visualization can detect issues that arise from incorrect rates or temperatures that can affect material properties, or you can not even track the errors due to uncertainties during the print process in the simulation processes. And as far as the high fidelity physical testing is concerned, it's very expensive and time consuming. So essentially, these 2 approaches are kind of expensive, and imagine like you have printed the entire object and then you realize that it doesn't meet design specifications. So you have wasted all these resources. So if we want to develop some techniques which directly analyzes the tool path, so we are started looking at the toolpath software verification, and in our literature survey, we haven't found any prior work in toolpath software verification. And just to give you a feel of where this lies in the whole 3D print design cycle, I'll be discussing the cycle here. So first, you create a CAD model of the object using a design software like AutoCAD, SolidWorks, or Maya 3D, and then this object files, this object files or the STL files are then imported to a slicing or toolpath planning software like Ultimaker, Cura, Slicer, or Simplify 3D, which then generates a set of instructions called the G codes, which are then fed into a 3D printing device firmware like Marlin, Clipper, and RepRap, which uses this G codes to print the 3D object. So as you can see, like there are these boxes which specify the stages, and theoretically each of the software components can be verified using traditional program verification techniques. In fact, there has been some prior work in the PL community by Chandrika Nandi and her colleagues who have looked at the design software phase, wherein they have developed this programming language called Lambda CAD, which synthesizes like a geometric design. But still, there is a major gap in the stage between the slicing and the 3D printing device firmware, which we have indicated using this red arrow. And this particular stage is very important because these are the actual machine instructions which go to the firmware for printing. And there are potentials for tampering and corruption which can lead to, which can disrupt the integrity of the print. So this is a very important stage that needs to be analyzed to maintain the integrity. So with this motivation in mind, the goal of our work is to detect whether the command sequence that drives the printer introduces subtle defects like misaligned exclusion or incorrect dimension. And the approach that we use to achieve this goal is to develop a direct interpretation of the G code such that the verification conditions which enforce some domain-specific constraints in the printing cycle can be checked at each step of the print as the machine state evolves. So the operating word here is as the machine state evolves. So we check during the whole evolution cycle. And to ensure that the bugs in our tool doesn't cause us to incorrectly verify a G-code program, we have taken a verified software approach where we verify every component of where we verify the core component of our analyzer, so that we have an absolute guarantee that whatever we are analyzing about the G-code is correct. Now this approach of doing toolpath verification is not very trivial, and to explain why this is not trivial, I will draw some parallels between the traditional program verification and additive manufacturing program verification. So in the traditional program verification realm, where we want to analyze some properties about, let's say, opaque compilers, we cannot directly do so because we do not know what the semantics of the compilers are. So it's not exposed to us. And in that case, what we have to do is we have to resort to some other kind of analysis called the binary analysis, where we analyze the output of the compiler against a semantic model of the machine. Similar problem arises in the additive manufacturing realm as well, where we do not know whether slicing and toolpath software is opaque, and as well as the 3D printing device firmware is opaque, which is the case for most commercial 3D printers. So in those cases, we cannot directly apply program verification techniques, and we have to resort to and we have to develop some analysis similar to binary analysis, where we analyze the output of toolpath planning software, which are the G codes, against a self-defined semantic model of the firmware. And the reason that I focus on self-defined is that, again, the formal model, semantic model of the 3D printing device firmware is not available. It's pretty, I mean, they have done it in a very ad hoc manner, so we have to mechanize or define this semantic model. Fortunately, most of these firmwares, they follow the standard called RS-274 standard, which was initially designed for traditional manufacturing and a subset of that has been later adopted for 3D printing. So we will be looking at that particular standard or a particular style of writing programs for manufacturing. So next I'll be discussing what this RS-274 standard is. So the RS-274 or the NGC language is based on a line-oriented execution model, where each line includes commands that can to perform a task like move the printer head in a circular arc or in a straight line while extruding the filament. And the words for these commands are called the G or the M codes, where G codes mostly operate on the physical state of the machining tool, like move it in linear motion or directed circular motion, and M codes mostly operate on the controller state, such as turn on or off the coolant or select the extrusion mode. So on the left-hand side of the slide, I have presented an example of what this RS-274 language looks like. So as you can see, these are a set of G instructions followed by some axis commands. So let's look at the first example where we print a square. So let's assume that the printer head starts from the origin of the coordinate system 0, 0. Now when we instruct G1x 1.0, what does is that it tells the printer head to move 1 unit in the x direction in linear motion. So G1 stands for linear motion. So each G command has its own specific meaning. So here, so then the printer head moves to 1, 0, then G1 y 1.0, then moves the printer head to the coordinate 1, 1. G1 x 0.0 moves it to 0, 1, and then G1 y 0.0 moves it back to the origin, which is 0, 0. So we have traced a square path. And as you can see, this G instructions, the G commands have caused the machining center to change from one mode to another. In this case, it's the physical mode. There are other commands which also lead to change in the controller state. And these commands are typically classified into 2 categories, modal commands and non-modal commands. So for the modal commands, some modes may remain active until this modal commands change it explicitly. Like for the example of these modal commands are G90 and G91 for absolute and relative motion. So if I go back to the example of the square, we have this G90 and G91 on top of the program. So what it does is that G90 says that the printer head should move in a coordinate system which is absolute or attached to the printer bed, and G91 stands for relative distance mode, which says that the motion of the coordinate of the printer head is with respect to the reference attached to the printer head. So essentially we have these two different distance modes, and another point to note is that we just write G90 and G91 once on the top of the program, but there is an implicit G90 attached before G91. So if you write it explicitly, it would look something like G90 G1 x1.0. So this G90 command is active throughout the program, and that is why it's called modal command, because it is active even outside, even after the line that it is specified. And this will remain active unless we say G91. So when we say G91, then the modes goes to relative. So essentially, yeah, we have both this G90 G91 remain active until either of them is specified explicitly. On the other hand, we have the non-modal commands whose effect is restricted to one line, to the line in which they occur. And yeah, so outside that, we do not have the effect of these commands. Now the modal commands are further arranged in modal, yeah?
So do these G codes, they only specify the location and don't specify the speed at which to move to the location?
So the speed is specified by another code word called F. So that stands for the feed rate. So it says that at what speed the printer head should move when the material is extruded. So you have other G commands and F commands associated with the speed. Okay. Yeah. 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 So these modal commands are arranged in modal groups. And these modal groups are pretty much independent of each other. So that means is that transition in that modal group will not affect the state of any other group. So on the left-hand side of this slide, I have presented two modal groups. One modal group is for the distance mode, and then the other modal group is for the feed rate mode. As you can see from the state transition diagrams, both the state transition diagrams are self-contained, and there is no transition from feed rate mode to the distance mode, so they are independent of each other. And the other thing about these modal groups is that some modal groups have a default G-code value. For example, the distance mode has a default G90. So what that means is that when you turn on the machining center, even if you don't specify G90 or G91, by default it assumes that the distance mode is G90. So all the motion of the printer head is now with respect to this absolute coordinate system. On the other hand, modal groups like the feed rate mode do not have any default G command associated, so it remains inactive if nothing is specified. And to say what kind of mode you want, you have to explicitly say G93, G94, or G95. So as you can see, like there are a lot of subtleties associated with how the modal commands transition from one mode to the other. And yeah, so we capture all of this in our interpreter using a state model. So here we track two states: the physical state, which was the position of the printer head, and then the modal state, which determines how the modes transition. And all of this are grouped into a machine state. So we have defined this using a record in Coq, which tracks both the physical and controller. So this machine state can be decomposed into physical and controller state, where the physical state contains parameters like the position of the printer head in absolute coordinate system and in the relative coordinate system, position of the extruder and whether the extruder is on or off, and also it tracks the path of the printer head throughout the printing process. The controller state, on the other hand, can also be decomposed into a physical state and a purely modal state, where the physical state determines what kind of physical parameters are associated with some of the G codes. So if you remember the example of the square, we had G1 x1.0. So that means that that x1.0 was the physical access parameter associated with that G command, and that forms the controller state. And there are similarly other kinds of physical parameters like coordinate offset that are associated with G92, and then the feed rate, etc. So this forms the controller physical state. Then the modal states essentially define the transition that happens between the purely modal commands like between, let's say, G90 and G91, and then G93, G94. So all those transitions are tracked by this modal state, and it also maps a mode in a modal group with associated G commands. So as you can see, we have this clean separation between the physical and the controller states, which was really essential in the design of a verified interpreter, because when we started with an initial prototype of the interpreter, which was a monolithic OCaml code implementing all of this in one machine state, it created a lot of issues with respect to verification when you wanted to use different tools for different parts of the interpreter. So this nice clean separation introduced a modularity, which was very helpful when we started doing the verification process. So next I'll discuss the high-level interpreter design. So our interpreter takes as input a G code and then parses it into an AST by following a priority order for evaluating the commands. And this is very essential, because if we do not follow a priority order, then it essentially leads to a misinterpretation, and the whole thing goes, it just blows up. So once we have this normalized, AST, which is normalized according to this priority order, we then pass it, we then define an interpreter step function, which is implemented and verified, and therefore forms a part of the verified core. And this interpreter step function walks through the AST and then executes the command sequence and generates an output state. This output state is then fed into the VC checker, or the verified condition check, which is also forms the part of the verified core. Now this VC checker, what it does is that it enforces domain-specific constraints, like the machine state is inside the bounding box, and if this output state satisfies this VC check, then interpreter step function steps through the next command sequence, and the process repeats until we reach the end of the file. And if this whole thing goes well, then our interpreter emits a execution trace, which essentially tracks the coordinate of the printer head throughout the print, which can then be exported and visualized to visualize the 3D model. However, if at any step the output set doesn't satisfy this VC check, then the interpreter terminates and it generates a failure report, which essentially details where things have gone wrong, and it has a very helpful message. Salient feature of our tool is that it's modular, which allows us to integrate more complex verification checks without impacting the rest of the interpreter. So for example, let's say you want to write a VC checker which does the collision detection, then you can seamlessly integrate that with our tool and without impacting the rest of the interpreter, and this gives a nice like modularity and you can compose things together. Yeah. So next I'll be discussing some of the challenges or the barriers that we identified during our verification process. As I mentioned earlier, we started with a monolithic interpreter, and so that was verifying that was challenging, because we could not use different tools according to the strengths to verify the interpreter. So we had to decompose the physical and the control states, and then this nice modularity helped us to verify parts. So once we achieved this nice modular design of the interpreter, we started verifying, and there were some specific challenges. The first challenge was with respect to I/O and parsing, which was notoriously difficult to model because the RS-274 standard does not provide a formal grammar for these G-code programs. So we had to carefully go through the manual and write the grammar. But we do not verify it yet. We focused our attention on verifying the core interpreter. And since these are not very critical, this formed the tested computing base. The second main challenge was that we started using these tools, Chameleon and Gospel, which do direct verification for the OCaml programs. But soon we ran into the issues that this tool Chameleon does not handle functized maps and has no floating point support. Furthermore, the Gospel, which is a specification language for OCaml, only handles a very small subset of OCaml and was not well suited for verification. So we had to move from direct verification to an indirect verification approach, where we used tools like Y3 to write parts of the interpreter in YML and then extract it out to OCaml. And furthermore, there were some issues with Y3, specifically with respect to floating point reasoning and extraction, which forced us to use tools like Coq to model the physical part of the interpreter. So what ended up happening was that we had to use Y3 and Coq together, and this nice diagram on the left-hand side shows how this dependency looks like. So the main property that we verified here is the correctness of the interpreter step function, which relies on a set of core libraries like logical operations, maps, and data structures, which model the modal states. And this maps and these green boxes were the ones that we have verified in Y3, which models the modal state. And then the yellow boxes, which includes the floating point operations and linear algebra operations, which track the evolution of the physical state, was verified in COG using the flock library. And once we had all of these structures verified in Y3 and COG, we extracted them out in OCaml and then integrated with other parts. So next I will dive a little bit into verification in both Y3 and COG. So I'll start with Y3. So as I mentioned in the previous slide, for the Y3 we have verified properties about the modal states. Here as well we had some challenges. The main challenge was that when we wrote our first design of the tool, it used functorized data structures like maps and sets to model the modal states and the transitions between the modal states. But Y3 has very limited support for verifying and extracting this functorized data structure, so we had to restructure our design and use the primitive structures like lists, which are easily verifiable in Y3. And this posed a trade-off between verifiability and performance. Fortunately, the list of modal states that we maintain is in the order of 10s and 20s, which did not impose like a large performance bottleneck, so we could trade performance for verifiability. And on the left-hand side, I have a small example on explaining how the verification in Y3 is done. So in this example, we write this function which verifies the membership of a string in a list. This list you can think of as a list of non-modal commands. So the properties that we verify about this string membership function is that first that this function terminates, which is easy to verify using variants. It is in this variant clause which verifies termination of the variant clause on the list, because and since the list is a finite, since we have a finite list, it's easy to verify by structural recursion on the list. And the second property that we verify is that the result from the string membership function indeed satisfies the mathematical definition of membership, which is defined using this mem predicate in the Y3 standard library. And once we have verified these two properties, we then extract the YML implementation into OCaml and then integrate it with other parts of the interpreter. So this is just one thing that I have shown. There are other stuff about how modal states are modeled and what kind of properties that evolve, which is a little bit more subtle than this. And the other thing, so the Y3 was about the modal states. Now we have used COG for verifying properties about the physical states, where we so in this case as well, when we started doing the verification, first we wrote our floating point operations in Y3, and then we tried to extract out the Y3 implementation to OCaml, but we ran into the issue that Y3 does not support extraction of floating point literals, and that was a major issue because we use floating point literals throughout our interpreter. So we had to abandon this Y3 approach for floating point arithmetic and then move to COG. Where we use the primitive floats in COG and extracted them to OCaml and use the flock library for verification. So in this slide, I have shown like a small example on computing the dot product of two vectors. So we define dot product in COG, we extract it out to OCaml, and the property that we verify about this dot product is that the dot product is finite, and we use the flock library for that, and we verify this using an assumption that the dot product is an overflow and each element of this vector is finite. So we use this example here is very simple, but we have used a similar approach to verify some other complicated properties about the linear and the circular motion of the printer head. So to summarize, so far what we have is a verified core library of the data structures and the linear algebra operations, and we have extracted them out and to get our verified interpreter. But there is another part which is the main driver code written in OCaml with effects, and challenge was the next challenge was how we propagate these effects throughout our core interpreter. And to do so, what we did was we modeled the effects in COG using monads, and one specific issue there was that we started with a generic type class definition, but we found out that this was not well suited for code extraction, and therefore we had to define a specific instance of the monad which models the intrinsic behavior of the effects in this additive manufacturing programs, so that we can tightly integrate the verified interpreter code with the unverified driver code. And yeah, this by doing so we achieved like a whole tool with verified and unverified components. So next I'll be discussing some results. So the first result that I would like to point is the number of lines of verified versus unverified code. So about 54% of the code base was verified in Y3 and Coq and extracted in OCaml, and the remaining 46% was handwritten and includes the G-code parser, JSON parser from configuration files, boot output functions, ASC generators, and petty printers. And we have tried to write them down as much as possible without depending on the third-party dependency, because eventually we want to verify them and minimize the trusted computing base and get more of the verified code base. If you look at the table, the other thing that you might notice is that the number of lines of extracted code in YML is much less than Coq, which means that we had to do a lot of manual verification. But that was because of the limitation of the library in supporting, especially the floating point arithmetic. And we communicated that with the Y3 developers, and they said that they will try to resolve the issue in the next versions of Y3. So once that is up, we plan on migrating as much of the code to the YML so that we can get more automation out of that. So the second result that I want to highlight is the results from the verification condition checks. So if you remember, in the high-level interpreter design, there was one box in the verified core about VC checker, which verifies some domain-specific constraints for the output state of the interpreter. So that we have currently in our prototype tool, we have two verification condition checks. One which says that the printer head is always inside the bounding box. So we check that the coordinate of the printer head is always inside the bounding box. And the second condition is that for the arc motion, there is no trajectory such that the printer head will ever be outside the bounding box. In this case, we do not explicitly compute the coordinate of the printer head. We using the input G codes and some of the complicated vector calculus that we have implemented, we predict whether the arc motion will leave the bounding box. And to demonstrate the feasibility of that, we have these two nice pictures where we show the detection of this arc motion violation for the bounding box. So what we did here was that we took a G-code command which prints a circular motion. So in the first figure, you have the whole arc inside the bounding box, which is represented using this blue trace. For the violation, what we did was that somewhere inside the G code, we inserted G91, which changes the motion from absolute to relative mode, and therefore after that G91 instruction, everything was all the motions were done with respect to relative frame of reference, and the coordinate updates due to that led the arc to go outside the bounding box, which is highlighted in this using this red trace. So the red trace essentially shows the toolpath that is outside the bounding box. So in this way, we have tested some of the G codes for the violation check detection. And the third main result that I wanted to highlight was the visualization of the 3D print itself. So in this case, what we did was that we took an STL file for a VAS, and we imported that in this classing tool called Ultimaker Cura, the visualization of which is shown on the left-hand side of the slide. So this Ultimaker Cura takes this object file, it slices into a G-code instruction, which is then fed into our analyzer, and the result on the right-hand side is the visualization of the path trace of the 3D printer that is emitted from our analyzer. So as you can see, like there is we have captured the whole design that was initially fed into an analyzer pretty neatly. And the best part is that all of this, like the code interpreter is verified, so we get this nice result from our verified analyzer. And the other thing that I wanted to highlight here was that which is a strength of our tool, is that we capture the whole tool path motion, which allows us to do some complicated VCs. So if you look, if you look at the diagram, there are two color codes. One blue, which says that which indicates the actual extruded material, and then there is also a red trace which shows the tool path motion without extrusion. So we capture both the extrusion and the non-extrusion tool motion, and by doing so, we get like the full toolpath motion, and then we can do some complicated VC checks like collision detection and those kinds of stuff, which is.
Could you look at the screen?
It's not that similar than Luke. Can you make a point and say?
Oh, right, sorry. Yeah. So in this
Go to the screen.
okay, sorry. Yeah. So essentially this dots were actually like red in my computer. So these are actually the motion without exclusion, and this nice greenish color is the extruded part, and then there are like some other stuff on the top which represents the non-excluded part. So essentially we have captured the toolpath motion without exclusion and with exclusion, and like the whole toolpath motion, and that allows us to do like full-fledged deep analysis on the toolpath planning part, which is not well supported in the simulation-based approaches. Yeah, so since we are at the FUNARCH workshop, so we have derived some of the architecture lessons from our experience. So the first lesson that we have derived from our experience is that modularity helps a lot in doing the verification. The fact that we were able to decouple physical and controller states allowed us to do verification using different tools like Y3 and COG. If one were to use some other tool, they can plug that in and do the verification because of the nice modular framework of our tool. And the second lesson was that at some point I have mentioned that we moved from functorized maps to the list-based maps. So in that case, we have we favored verification over performance and use structures which are amenable to verification. And the reason that we were able to do that was that we did some evaluation of the performance differences, and we found out that it was not too high. And similarly, like if you go beyond beyond the additive manufacturing into some generic function programming, where you face a similar kind of trade-offs, if the performance difference is not very high, then it would be nice to use data structures which are more favorable for verification. And the third thing was that we try to reduce as much of the third-party dependency as possible and write as much of the code on our own. So just to give you a little bit, to give you numbers, we have like about 360 lines of 110 stream parser and 100 lines of parser commenter library, and which we eventually want to verify. And by reducing the third-party dependency, it allows us to do verification without having some additional challenges. The next major architecture lesson that we learned was regarding modeling effects. So here we evaluated the generalizability of modeling effects and tried to leverage as much of the inherent behavior of the system by developing a specific instance of this monads to propagate effects, which allowed us to smoothly interoperate between the verified and unverified components. And this is something that often comes up in other functional programming projects as well. To conclude, the primary focus of our work was on the design of a verified interpreter for additive manufacturing program, and we achieved that goal by focusing on decomposing the machine state into physical and controller state to facilitate modular verification. And then in the end, we highlighted some of the architecture lessons in generic functional software design. In terms of the future direction, we have started looking at some of the, we have started pursuing some of the directions, and some of the directions are something that we have will be focusing on in near future. So the first direction is implementing some complicated verification checks like collision detection using KD trees data structure. So we have implementation of this KD data structure in OCaml, and we plan on mechanizing that and integrating that with our tool. The second direction that we want to pursue is about modeling uncertainties. Uncertainties can arise throughout the print cycle. It can come from the motors, from the discretization of the motors or other physical noise, and to get some accurate guarantees on the error in the printing process, we want to model these uncertainties, and that's something that is on the near horizon. The third thing that we want to pursue is implementing some vendor-specific extensions to Jiggle for 3D printing. So these these commercial 3D printers, they come up with some vendor-specific extensions, and to make our tool generalizable for analyzing the output of those print process, we want to model the behavior of these extensions. And the fourth direction is automating as much of the proof process as possible, preferably by developing some high-level program logic for this 3D printing process based on what we have learned during our mechanization of the G-code semantics. With this, I would like to conclude, and yeah, thank you everyone for listening to my talk, and yeah, I'm happy to take any questions. Thank you.
Thank you, James Chapman, Input Output. So I think I've got a couple of questions, but so one thing I was wondering about was the kind of correctness property that you're proving. So you talked about, I saw that you showed an example of a small component, and with the correctness property for that it was correctly capturing list membership, I believe. So that obviously gives you the kind of that each of the smaller components are well built, but what's the high level property?
Yeah, so the high level property is that like for the given input state that an interpreter step function takes in, we want to say that we want to say that the invariance. So there are some invariants, like there are modal state invariants, which talks about how the modal state update needs to behave, and then there are some physical state invariants, like at every step, the vector that we get, the physical vector for the coordinate, is finite. Like we do not get any nans or any infinities, etc. Like some exception for important values. So with physical state invariants, we maintain that all of the resulting vectors, like at every step, the state has those finite values. So those are the kind of invariants that we want to maintain both for the input and the output, and that's something that we verify. And the second thing that we verify is that is about the parameter handling process. So if you remember the square example, we had G1 x 1.0. So a value, so that's a valid G code. But let's say you just mentioned G1 and you skip the x 1.0. So that is an invalid G1 command. So those are some of the properties that we check as well, correctness properties. And then when you make state transitions, you would want them to be contained inside the modal group. We do not want any transition from one modal group to the other modal group. So those are the kinds of behavior that we want to capture in our correctness property. Yeah.
So I'm wondering if this approach is also applicable to subtractive manufacturing. Because I think subtractive manufacturing is a lot more, I would expect it to be more difficult than additive manufacturing.
Right. I mean, both subtractive and additive manufacturing, they have the same style of writing. So the NGC, ISO74 NGC language, that same language is also used for the conventional subtractive manufacturing. So this analysis can also be extended to subtractive manufacturing because they have the same flavor of writing. And even the G code means, like some of the G code have the same semantics for both conventional and additive manufacturing.
Yes, but I'm not sure. I guess with additive manufacturing, it's typical not really a problem that your printhead, in this case, will bump into the object that you're printing.
I mean, there is a possibility that it can happen.
Okay.
Yeah.
But
For
is
example,
that...
like, if we do like a rapid motion from one point to the other point, it can happen that
that's true.
The rapid motion it's not like it goes in linear motion. It can go like zigzag in any fashion, and it might happen that it can bump with the object in that case. So there is a possibility that there is a collision between the printer head and the object.
Okay, thank you.
Yeah, thanks.
One thing I was wondering is, it's interesting that you didn't find any prior work about taking a software verification approach to this kind of problem. But I think there is quite a bit of prior work about software verification of plans for robotic arm movements and that kind of thing.
Right.
And I wondered whether there were interesting similarities or things to be transferred between the fields there. Did you think about that at all?
Yeah. So I mean, there are some similarities, except that those arm motions. So here we are targeting like a specific style of the language, which is this RS-274 language.
Yeah.
So here essentially our front end was like this particular language, and we developed our interpreter for that language. But then there are some similarities about how transitions happen, which can be extended to the arm motions as well.
more questions?
So one thing on your motivation slide, I thought you said that you can't verify a compiler. I mean, surely not, right? So you said sort of traditional program verification, but there are things like CompCert, so maybe I must be missing the point. So CompCert is, being a verified C compiler, and there are other approaches where you can take a grey box approach, and each compiler step would output an abstract syntax tree, and you could check if it's doing the right thing. So, yeah, I thought I must be missing something.
CompScript try to model the semantics of the C program. There they have written explicitly how the behavior looks like. But imagine cases like where you do not know what the behavior will look like, and and then especially the scalability issue as well, verifying every R process and stuff, and mechanizing semantics and all.
Okay, and I guess, of course, I mean, when they designed CompCert, they started from scratch. They didn't take something like GCC and then try to verify it after the fact. So, yeah, okay, interesting.
Yes, I have another question. I was wondering, so my background is in, well, runtime verification, and I was wondering if there's effort, not necessarily with your research, but in general, if there's an effort in actually trying to check if the machine at that specific moment is still doing what the G code describes. As in, continuously check that it's not, steering away from what the G code describes the machine should do.
Right, yeah. I am not aware of that work. I mean, I have to look at the literature and see if there are some runtime approaches for those kind of things. Yeah, but I'm not aware of that now.
Okay, thank you.
Thank you for the talk. You said that in the RS-274 that it didn't provide a grammar. Can you describe, was that a problem for you, frustrating in any way, or were you able to kind of reverse engineer it yourself?
Right. Yeah. So that's a good question. I mean, this was an issue, especially given that the language was initially designed for conventional manufacturing. So it was not designed for 3D printing. So when you look at the extrusion, there is no G command as such for the extrusion. But we were able to do some search, and we found some blog articles where they used the existing G commands like G92, which is used for coordinate reset, to do the 3D printing stuff by extending the axis parameter with another E axis, and then you can do some sort of combinations between the different G commands to model the extrusion and those kinds of stuff. So it was not very clear. It is not specified in the standard itself. So we had to do some digging around and try to make sense of what's going on by looking at some of the open source firmware code as well. So yeah, that's what I meant. But yeah, no clear grammar.
That ties into the last question I wanted to ask, which was also about the standard. So given that the standard has this ambiguity, have you considered either proposing to update the standard or come up with a new one? I mean, if it's an ambiguity, perhaps it could be a sort of more minor update, or maybe there are other things that could be improved.
Yeah, that's a good question. So we are writing a paper on mechanizing semantics, and then once we have once we also integrate some other G commands, like this is a small subset, and there are other G commands as well. Once we have done a sufficient like mechanization of the G commands, we might try to contact the standard writers and maybe try to integrate some of those things.
Great.
Any more burning questions? We've got 2 more minutes before lunch. No? Well, let's get a 2-minute